So we're going to sample from this distribution. The distribution of pennies starts, you get some in the 40s, 50s maybe, but mostly it starts in the 60s. Now this is not necessarily a normal distribution. In fact, it's far from it. It's skewed which way, to the left or to the right?
Left.
To the left. Mostly we would expect something out of the 90s, maybe something out of the 80s when you sample from this distribution. But come up here to this box that says show sampling options. Click that. And then we're gonna set the number of samples to be 1,000. We're gonna take 1,000 samples of size 2 from this distribution. So I'll give you a second to set those up. Now our goal here is to take a sample of size 2, add them together, divide by 2, so you get the average age of that sample. And I want to look at the distribution of the sample mean now. How does that look? Does it look anything like this distribution? In fact, if you got a second here, let's take a couple notes of what we get from this distribution. The mean of this distribution is 86.736, and the standard deviation is 9.608. So I want to take note of those things. 86.736, and standard deviation is 9.608. And I've given you a spot to put those on that Google Sheets document that I sent you. In fact, there we go. We already got the mean and standard deviation here. So we should be good. We're going to take a look at what happens when we take a sample of size 2, 4, 9, 16, etc., and see what happens to the distribution of the sample mean. So there we go. When you're ready, you can click Draw Samples, and it's going to draw 1,000 samples of size 2 out of your distribution. It's going to look at the data, calculate the average age, and that's going to be 1 point. And when we do that, here's the most recent sample. Shows we drew a coin from 1984, another one from 1978. There's your 2 points, and results in a mean value right there. Mean value in this case would be 81. So falls right there. Let's look at the distribution of the sample means now. Now this is a new variable. It comes from this population, but it's a new random variable. Is that random variable does it have a normal distribution here? No, it doesn't. In fact, if you want to, what you can do is underneath here, it says overlay normal distribution. Does that look like it's a good fit? Now, I'm guessing and hoping that your numbers here are going to be a little bit different than my numbers. Is that true?
Yes, mine are.
Yes, I was a little concerned, but
yeah, it's nothing to worry about, because what's happening is this is a simulation. You're getting your own data. Your data is not going to perfectly match mine, but I bet it's close. So let's write down the mean and standard deviation for samples of size 2. So I'll put that with my Google Sheets. For samples of size 2, I had a mean of 86.863, and a standard deviation for me was 6.662. Now, before we did any of this, before class got going, I made a prediction here that the standard deviation was going to be 6.79. What do you think? Was I pretty close? Does that look pretty close?
Yeah.
Yeah, that seems pretty good. Let's see. If you calculate it on a percentage basis, I'm within about 2%. That's pretty good, considering I did this, you know, actually last night. So was it close or not close? Yeah, it's close. Does the distribution look normal? I'd say no. So I'll put a 0 here. Let's try this again with a larger sample size and see what happens then. So we'll go back here. This time we're going to reset our distribution to be samples of size 4. I still want 1,000 samples, so we're okay there. When you click draw samples, it should give you some new data. And let's write down that new data. Now again, I'm getting a mean that's close to my population mean, but not exactly the population mean. Let's put that data in our Google Sheets. 86.874. And this time the standard deviation was 4.673. So what do you think? Was I close here? My prediction that I did yesterday before you started doing any of this work?
Seems pretty close.
Yeah, I'd say it's probably within, 3% or so. So again, not bad at all, considering these things are happening at random. So again, it's close. But is it a normal distribution? We get a normal distribution. Yeah, it's better. Is it normal? Well, let's get rid of this for a second. It's not perfect. It's still skewed a little bit to the left, a little bit short on the right, but it's looking better. Okay. How are we doing so far? So in the back of your handout for section 6.3, we saw this, that you could start out with a lot of different distributions, doesn't matter how they look. And when you start sampling from them and calculating the sample mean has its own distribution. Now, when you have this one up here in the middle, which is skewed to the right, is your parent population. It's parent with a small letter p. Then you get this for the distribution of the sample mean. The sample mean is its own random variable. The value that you get depends on chance. And it kind of smooths out this curve a little bit when you look at that distribution. Is it a normal distribution? No, not really. When you increase the sample size to samples of size 10, the sample mean, it's starting to look a little bit more normal. And by the time you get to samples of size 30, it's looking really normal. If you had a uniform distribution to start with, like over here on the right, then again, after a large enough sample size, the sample mean has an approximate normal distribution. Now, those are a couple of distributions that are somewhat far from normal. If you started out with a normal distribution, then the sample mean will continue to have a normal distribution. So there's a couple ways in which the sample mean can have a normal or at least approximately normal distribution. So let's discuss those two different ways. So we're down here. Conditions under which the X bar has a normal or at least approximately normal distribution. And there's two possibilities. The first is that if you're starting out with a sample size which is large enough that a sample is size 30, when you take a sample of this size, the sample mean is going to have an approximate normal distribution with the same mean as your parent population, but the standard deviation is going to be a little bit different. Standard deviation in our parent population was sigma. Standard deviation in the distribution of sample means is going to be sigma divided by the square root of n. So you might have been a little bit curious how I could make such a good prediction of what you would see when we did that simulation. Well, let's take a look back here. So let's go back to our central limit handout or central limit Google Sheets. The formula that I plugged in here would be this number divided by the square root of the sample size. So if you click on this cell, you'll see exactly what I did. I took this number here, which is the standard deviation of our parent population, and divided by the square root of our sample size. So that's how I was able to get such a good prediction. And it worked pretty good. I think I was off by no more than 2% in any of these. Actually, for samples of size 9 here, I was within 1%. So yeah, we got really good results here. Now your results are going to vary a little bit from mine, but again, the values that you got should be pretty close to the predicted values. Let's go back to our handout. The other condition under which X bar is going to have a normal distribution is if you start out with a normal distribution. If you start out with a normal population, then regardless of the sample size, X bar is going to have a normal distribution. So same mean as your parent population. The standard deviation, just like the above condition, is going to be sigma divided by the square root of n. So you start out with standard deviation of sigma. The new standard deviation is going to be sigma over square root of n. Let's understand a nice little feature about that. And that nice little feature is that it's going to change our standard deviation when we increase the sample size. Can anyone remind me what we do, or excuse me, what the standard deviation represents? What does it tell us about a distribution?
How spread out the
Distance away from the mean.
Oh, excellent. I got a whole host of answers. You guys are making me look good. Yeah, it's how spread out you are from the mean. So if I decrease my standard deviation, then I should see less spread in the data. Let me just go up here to the projector or to the tool icon and click projector mode. I think it shows up a little bit better there. And I'm going to decrease the standard deviation. Right now, I've got it set at 2.34 for this particular graph, but let me decrease it and watch what happens to the curve. It's getting more and more centered around the mean, which in this case I have set to 0. Doesn't matter where you set the mean. Changing this parameter here is just going to change the shape of the curve. Changing the mean, which is denoted by the M in this one, changes where it's centered. But this changes the shape. So if I increase standard deviation, then the data is more spread out. This is a nice consequence of taking bigger and bigger samples. You're reducing your standard deviation. If I'm trying to estimate something, suppose, let me change the mean here to 2. There we go. Suppose I'm sampling from a population and I'm trying to figure out, well, what's the average age of kids in this group? And the average age is 2, but I don't know that. I'm taking a sample. By taking larger and larger samples, I'm decreasing the standard deviation, and I'm more and more likely to get a value close to the population mean just because I'm taking a large enough sample size. That's a good thing. I want to know what the population mean is. I take a larger sample size, and I'm bound to get something close to the population mean. If you don't take a large enough sample size, let's take a look here. If I increase the standard deviation, am I likely to get a value close to 2 if I sample out of this distribution? not as likely. And the more and more I spread out the area in this curve by increasing the standard deviation, the less likely I am to get something close to 2. But if I'm determined to get a good sample estimate of the population mean, there's one quick answer: increase the sample size. That decreases the standard deviation, and you're likely to get something very, very close to the population mean. So how does that translate into problems? Well, let's take a look here. There's going to be standard problems that you're going to see for the work in this section, and they're going to look a lot like example D here. And I know that's not exactly in order. We can do some of the other ones too. But this is exactly the kind of problem I want you to be able to solve for the exam, is something like this. So there's going to be a couple different parts. One is that they're going to ask you to work with a regular distribution. The other one is that they're going to ask you, do you understand what the central limit theorem is saying? So let's warm up with part A. And looking at part A, let me note for ourselves that Coke cans are filled so that they have a mean of 12 ounces and a standard deviation of 0.11 ounces. So example D. Now they don't say anything about this being a normal distribution, but we're going to have to assume it's a normal distribution. Otherwise, you're not really going to be able to make any headway in part A. So let me start by writing this down. X is distributed normally with a mean of 12 ounces and a standard deviation of 0.11 ounces. They ask us for the probability that X is greater than, what was it, 12.19, I think it was? Yes, 12.19. That's part A. That's something we can get from Google Sheets or from StatDisk. If you're doing it in StatDisk, you have to first compute the Z value. You'd have to do Z equals 12.19 minus 12 over 0.11, and then put that Z value into StatDisk. I'm just going to use Google Sheets. You could also use a graphing calculator. Let's do it. So with Google Sheets, we're going to be using norm distribution equals norm distribution. This can be our value of X, which is 12.19, the mean, which is 12, the standard deviation, which is 0.11, and then true. Now that's going to give me the area to the left. And maybe I should draw this here. That center value would be 12. Then 12.19 is here. What area should I shade for 12.19, or X is greater than 12.19? Do I want the area to the left or the area to the right? Which one should I shade?
To the right.
To the right, good. So that gives me a little bit of a problem here in using Google Sheets, and that is Google Sheets is going to give me the area to the left. I want the area to the right. In fact, in just drawing this, I know that this area has to be less than 1/2, right? Because it's to the right of 12. Half the area is to the left of 12. All right, so what are we going to do to fix that? How can I work around the fact that I'm getting the area to the left?
Subtract it by 1.
Yes. So we're going to subtract this area from 1. Let's do that. Up here. So I'm just going to open up a new sheet, a new tab. Equals. Now you can do it all in one shot. You can do equals 1 minus norm distribution of 12.19, comma 12, comma 0.11, comma true. Let me leave that up there for a good few seconds in case you're trying to copy that down. But that should give me the exact probability that I need. Now, at least one little double check on this is that my probability should be less than 1/2. If it's not less than 1/2, I absolutely know I made a mistake. So what's the nice happy ending I'm going to get here? What's the answer when I'm going to press my button?
0.042.
0.042? Do we agree with that?
Or 0.0421.
0.0421?
Yeah.
Thank you so much. And we got some agreement. So yeah, 0.0421. In fact, I like the way you rounded it off. Thank you so much. 0.0421. So I'm just going to do it this way. I'm going to do equals 1 minus all that, approximately 0.0421. So is there a good chance you're going to get a lot of extra pop out of your can of Coke?
No.
Not really. In fact, I would say that that's, an unusual event. The author of our book says that something less than 5% really starts to mean that this is an unusual or significant event. So, okay, hopefully we're good with that part.
Okay, I have a quick question.
Yeah, please.
So when I did like the norm distance or like the I got a 1 is the answer.
Do you have all this filled in the exact way I do? And did you remember?
Yeah, because I have 12.19 and then the mean is 12, the standard deviation is 0.011, true.
Oh, it's 0.11. It's not 0.011.
Oh, sorry, thank you.
There we go. Awesome. Yeah, my bad. I should have made that look a little bit more like a decimal point. Let's take a look at the second part of this. And the second part is really asking you, do you understand the central limit theorem? So in the second part, it says 36 cans of Coke in this data set been selected. They have a mean weight. Find the probability that 36 cans of Coke have a mean at least 12.19 ounces. So what's different is that you're no longer talking about the standard deviation of, or excuse me, the mean and standard deviation of this. We've got an entirely brand new random variable. So I'm going to call it X bar sub 36. So it's the mean of a sample of size 36. And now we got to figure out, well, what's the distribution? Well, for that, let me go back to our handout. If we start out with a normal distribution like we do here, then the sample mean for samples of size n is going to be distributed with the same mean as our parent population, but the standard deviation is going to be sigma over the square root of n. So let's look back here. This is our parent population. Because this started out as a normal distribution, it's going to have a normal distribution. Or because we have samples of size greater than 30, it's also going to have a normal distribution. So in one of two ways, you can realize that this has a normal distribution. Its mean is going to be the same as this one. So those two numbers are going to be the same. What's going to be different is the standard deviation. The standard deviation here is going to be 0.11 divided by the square root of 36. Can anyone suggest a reason that they chose 36 as a sample size?
Is it because it's over 30 and then it starts to look better?
It's over 30, and it also, square root of 36 simplifies very easily, right? It's just 6. So it's just easier to work with. So normal distribution, mean of 12. If you calculate this out, 0.11 divided by square root of 36, which is really 0.11 divided by 6, you're going to get 0.0183. 33333. I'll put another 3 there, but that's the distribution you're going to work with. So you've got a new distribution, but it's the same problem. We're still looking for the probability that our observation is greater than 12.19. I'm guessing that the chances are a lot slimmer here than they were here. Why is that? What happened to the standard deviation? Well, standard deviation got smaller, right? We went from 0.11 to 0.0183. So I've got a new distribution. It's going to be taller and narrower. So it's less likely that I'm going to land out here in the tail. I'm more likely to be closer to 12. From here, it's the same problem as it was just a minute ago. I still want to find the area in the right tail. It's going to be 1 minus norm distribution of 12.19, comma 12, comma 0.01833, and then true. So that should be it. Let's check it out. So I'm just going to copy this and paste it over here and change just the one number that I need to change. I'll do 0.101833. And it's essentially 0. Wow. So basically there's no chance that you're going to get 36 of them that are overfold by that much. It's just not going to happen. So even Google Sheets doesn't do anything except round this to 0. I'm sure that if we had enough significant digits here that you'd probably see something, but it'd be incredibly small. Are you guys able to get the same conclusion here for us?
Yes.
Yep.
All right, awesome, awesome. So we'll continue with this one. And, you know, I've said it before, I don't like the fact that they kind of denude these problems. They take away anything that might be of interest. The weights of a certain brand of candies are normally distributed with a mean weight of 0.8586 grams and a standard deviation of 0.0516 grams. Can anyone guess what candy that they're talking about and not really mentioning by name? Give you a hint, we worked with it in this class before.
M&Ms.
M&Ms. Yeah. So M&Ms have this distribution in terms of weights. We're going to take a look at the probability that if we select one, that the candy weighs more than 0.8534 grams. So that's the probability we want to look at. X greater than 0.8534. That. So let me draw our distribution. And let's see. So something like this. In the middle of that distribution, I'm going to draw 0.8586. And then in here, I also need to squeeze in 0.8534. Now, am I looking for the area to the right or to the left of that?
To the right.
To the right.
Right, good. So I want to find this area here. That's the area I'm looking for. So how are we going to do that? Well, you could calculate a z-score and do it directly on StatDisk. There's nothing wrong with that. The z-score you would use is z equals this minus this divided by that. If we do it with Google Sheets, let's save a little room here next to that equal sign. I'm going to write norm distribution of what? What should I put in there? Someone help me out.
0.8534.
All right, 0.8534. Good.
0.8586.
0.8586.
0.0516.
Excellent. And then
1 or true.
true. Excellent. Now, there's one problem with what I just wrote. It's not going to give me the probability that I'm looking for. What's it going to give me?
If it was looking toward the left, so you have to minus it by 1.
Exactly. So that's why I suggested leave a little bit of room here. We got to do 1 minus that so that we get the area in the right curve, not the area in the left curve. Let's take a look at what that probability is. Now, keep in mind, based on the drawing, you should have a certain expectation for this probability. At the very least, this probability has to be greater than what? Anyone know?
0.5.
Has to be greater than half. Thank you, Amanda. Has to be greater than 1/2 because it's to the left of our mean and half the area is to the right of the mean. So we have to have something greater than 1/2. Equals 1 minus norm distribution 0.8534. This is kind of annoying. 0.8586, comma 0.0516, comma true. Boy, that's a long one. So I'll leave it up there for a good few seconds there in case you're trying to copy it down. What this number turned out to be?
0.5401.
0.5401. Sounds good. Thank you. So again, it's equals 1 minus norm distribution, 0.8534, comma 0.8586, comma 0.0516, comma true. And Shira spot on again. Thank you. Are we okay with that first calculation? Let's take a look at the second part of this problem then. If 464 candies are randomly selected, find the probability that the mean weight is at least 0.8534. So now we've got something different going on. And the key thing to see here is that we're talking about 464 candies and their mean weight. So the mean, the sample mean has its own distribution. So let's figure that out. So for part B, it's going to be X bar for samples of size. Oh, rats, where did it go? Samples of size 464. So I like to write that 464 here just to remind myself. You don't have to. These are going to be distributed normally the same distribution in terms of the mean, 0.8586. But somebody I haven't heard from yet, tell me what the standard deviation is going to be. How is that going to change? What's it going to be, or how am I going to calculate it? Okay.
Is it 0.8586 divided by square root of 464?
Close. We are
Or
going to
just
divide by
regular
square root of
464?
Whereas we are going to divide by the square root of 464, but we're not going to divide 0.8586 by square root of 464.
Oh yeah, 0.0516.
There we go. Awesome. Thank you, Alexander. 0.0516 divided by the square root of 464. And you know what? I'm going to get a little bit lazy here. I'm not actually going to do that calculation myself. I'm just going to let Google Sheets do it. Okay. So let's think about what's going to happen here. In this particular problem, we've got a new distribution. And because we have such a large sample size, it's going to mean that this is going to be a tighter curve. So I'm expecting this probability to be higher than this one because it's being pulled in, it's being squeezed. It's not as spread out as it was before. So I expect a higher probability when I do this calculation. I'm still trying to find the area to the right. This just should be more of it than was in this first example. But you're still trying to find an area in the right tail, which means you're going to do 1 minus norm distribution. Now you've got a couple options. Nothing wrong with just taking 0.0516 and divided by the square root of 464. Nothing wrong at all with putting in 0.002. Now actually, yeah, 240, actually 24. If you round it to this decimal place, that gives you a 1, which on the top of the 9 gives you a carryover to the 4, whatever. If you don't feel like rounding it, hey, then pay attention here because we're going to avoid rounding it. 1 minus norm distribution of 0.8586. Oops, no, wrong number. My bad. What number should I have here?
0.534.
Yeah, 34. In fact, I'm going to do it like I did up here. This number, I'll put all in red. So 0.8534. Ah, that's terrible. That is a 0.8534. And then 0.8586, comma 0.0516 divided by the square root of 464. Now, if you don't feel like just putting in the number 0.0024, I get it. That's a nice easy fix, but you can just put in square root SQRT 464, comma true. And I don't know if you regard that as a handy workaround or not. It means you don't have to bust out your graphing calculator. That's an 8 there. Equals 1 minus norm distribution 0.8534, comma 0.8586, comma 0.0516 divided by SQRT of 464, comma, true.
I think you missed your decimal place on that 8586.
I did indeed. Because I was looking at that going, you know, I expected something bigger, but not exactly one. So you're exactly right. Are you guys getting the same thing here?
Yeah.
Yeah.
Yes.
Thank you. Thank you. Now let me copy it over, and for comparison's sake, let's just say that instead of putting it in this way, I just put in my decimal approximation that I did with the graphing calculator, 0.0024. And let's see if that makes a big difference. Not a huge difference by 2/10,000ths, so not a big deal, but you know, I guess I kind of like this. I don't want to burden you with technology. So if you don't feel like doing it that way, don't worry about it. This will be close enough. There should be some tolerance built into your answers. How are we looking on that one?
So I got 0.5333. I'm not sure why.
If you want to put your Google Sheet command into the chat, maybe I can take a quick look at it.
To my iPad, but it's so I did 1 minus norm dist 0.8534 and then 0.8536 and then 0.0516.
Wait. It should be 8586 for the second term.
Oh, there it is. Thank you. Sorry.
Sure, no problem. Anyone else struggling in it? Let me highlight my calculation here so that you can see it again. Now we've seen a couple examples like this, and these are what really a lot of your problems are going to be like, is kind of a part A in which you don't have to use the central limit theorem, and a part B in which you do. Part A, basically you've got a sample size 1, so just sampling from that distribution. Part B, you have to use the central limit theorem, which basically says that you're going to have the same mean, but the standard deviation is going to be divided by the square of the sample size. That's the big part there that you've got to get, is that you're changing the distribution. It's no longer nice and spread out. It's getting squished. Well, that's a nice scientific term for us here. Squished. Standard deviation is decreasing. So all that probability is piling up closer and closer to the mean. Are you guys ready to try one? All right, that didn't inspire me. All right, let's take a look at example B. An airliner carries 350 passengers, has doors with a height of 72 inches. Heights of men are distributed with a mean of 69 and a standard deviation of, I'm trying to remember what it is, 2.8 inches. So let's start by copying that one down. B. X is distributed normally with a mean of 69 and a standard deviation of 2.8. If a male passenger is randomly selected, find the probability that he can fit through the door without bending. So I guess I assume that he's walking through barefoot, not with his shoes, but that's okay. Want the probability that, let's see, how tall is the door? 72 inches. So we want the probability that X is greater than 72. Like the last one, let's draw this. What should I label that center line with?
69.
69.
Yes, 69. Perfect. Now I want the probability that X is greater than 72. So, that's going to be out here. That's more than one standard deviation above the mean. So it's going to be out here. 60, 69, or 72. Which way do I want to shade in this one? To the right or to the left?
To the right.
Right.
Yep, another one to the right. So I want to find the probability of X is greater than 72. So back to norm distribution. So I'll give you a second to think about it. Try and write down the command that we need to calculate this. Yeah, so thank you. And actually looking at this, we do want the probability or the area to the left because we want the passenger to be able to get through without bending. That means that the passenger's height is less than or equal to 72. So I want the pink area here. So, oops. Thank you so much. Probably that X is less than 72. Good deal. So let's figure out what this command is going to be to find that area. Well, I'd want the 72 here, and then the mean and standard deviation, 69 and 2.8. And then what always follows it with this command?
True.
True. Good. Now, before I put this up, or before I find that answer, let me ask you what you expect for as far as the answer. Is it going to be less than 0.5, equal to 0.5, or greater than 0.5?
Greater.
Greater.
Yeah, it should be more than 0.5, right? So if you get something less than 0.5, then there's something wrong. So it's not a complete check on your work. You could still get the wrong answer, but it's a flag. If you got something less than 0.5, you absolutely know that you got something wrong. There's a mistake someplace, and it gives you a chance to find it. All right. Equals norm distribution, 72, 69. I like the numbers in this problem much better than the numbers in the last problem. That was annoying. And true. Perfect. 0.8580. Let's move on to part B here. If half of 350 passengers are men, find the probability that the mean height of the 175 men is less than 72 inches. So again, you should be getting used to the pattern in these problems. The first part deals with the distribution. The second part says, oh, now we're going to deal with the distribution of the sample mean. What was the size of our sample? How many men did we have?
Was it 350?
350.
175.
350, but divide that by 2 because half of them are men. So 175. See if you can't write down the mean and standard deviation of this new variable. Let's look at that together. So what would the mean be? What would the standard deviation be? Two things I need to know.
The mean is still be 69.
All right, thanks. The mean is 69.
And then standard deviation is 2.8 divided by the square root of 175.
Perfect, perfect. So basically we're gonna repeat this calculation, except we're gonna have a new standard deviation. That standard deviation here is gonna get replaced by this one here. So equals norm distribution 72, comma, 69, comma, let me do this in red, 2.8 divided by the square root of 175. So that's the big change from up here, and then true. My guess is that we're probably evenly split between doing this on Google Sheets with a square root command and dividing it with a calculator. So again, it's up to you what you're most comfortable with. So equals norm dist 72, comma 69. Did anyone beat me on this? What'd you get?
1.
1? Okay.
I got 1 too.
Me
Sounds
too.
about right. Can anyone understand or make sense out of why we got a 1 there? Can anyone understand what's going on there?
Seems like all of the answers on B is either 0 or 1.
A lot of them seem to be working out that way, but let's understand why that's happening here. 175 is a pretty big sample. Square root of this is something a little bit more than 13. So 13 is going to go in there a lot of times. Or this is a really small number compared to 13. And what's happening is that the standard deviation of our new distribution is really, really small. And the probability that for this new distribution, you get something out here past 72, it just vanishes. It's just too small. Actually, let's take a look here. Might not be a bad idea to calculate the z-score for this. So let's take a look. Z equals x, which is 72, minus 69, divided by standard deviation, 2.8 over square root of 175. So I'm just going to calculate the z-score and find out how unusual that is. Now, do you remember the empirical rule? Empirical rule told us how much data was within 1 standard deviation, 2 standard deviations, 3 standard deviations away from the mean. 1 standard deviation. How much data was within 1 standard deviation of the mean?
68%.
Excellent, 68. And then what?
95.
95, and then 99.7, I think. 3 standard deviations away from the mean. I'm guessing that we're beyond that. So let's see, that's going to be, I'll just do it all out. Parentheses 72 minus 69 divided by parentheses 2.8 over the square root of 175. Oops, I'm at 175. Wow. You're 14 standard deviations away from the mean with that number. It's no wonder that there's no area out here. That's crazy. I mean, think about it. 3 standard deviations, you've got almost 100% of your data. 14 standard deviations, wow. Not a shocker that she just sort of throws up a 1. It's like, no, you're gonna get people, or you're gonna get an observation that's less than 72. All right. There's a part C to this as well. And this one's just kind of a thinking one. When considering the comfort and safety of passengers, which result is more relevant? The probability from part A or the probability from part B? Why? Which one is more relevant? Think about who's going to be walking through that door. Am I going to have one person at a time walking through that door, Or am I going to have the average person out of, I'm going to take 175 men and create this average person and march that average person through the door? Which one's really going to happen?
Probably A, because it's more random.
I agree with you on A, but the reason is, and maybe I didn't do a good job of dramatizing it, is that you're only going to be marching one person at a time through. It doesn't matter what the average of 175 men is, they're still going to go through one person at a time. So that's the more relevant probability. This is just kind of a fun exercise. It's a good illustration of the central limit theorem, but it doesn't really have much bearing on this problem. What you're going to be concerned about and watching is that, these are the people that are going to be walking through. Are you comfortable with that last conclusion, the part C?
Why was it more relevant again?
Because people are going to be coming in one person at a time. You're not going to create some kind of monster person out of 175 people and march an average person through. They're marching through one at a time, not as the average of 175 men.
Okay, thank you.
Mm-hmm. Anything else on this one? Keep in mind that all the problems that you're going to be facing in this area, not all, but most of them are going to be just like this. We're going to start out with a basic probability, and then one for which you're going to need to apply the central limit theorem. All right, let's stop things here.